In this video we're going to look at the most oxidized form of an alcohol, which is called a carboxylic acid. So once you oxidize an alcohol completely, we can make this thing called a carboxylic acid, which is defined by having a COOH group, okay, which looks like this on the end of a carbon chain. So these are generally weak acids, so things like vinegar is a famous one, which is ethanoic acid. And because they're weak acids, only partially form the H3O hydronium ions in the solution. They can be synthesized from complete oxidation of a primary alcohol, which we'll look at in a moment. And the reason these are so important is because of their many uses in production of different chemicals, in the pharmaceutical industry, the food industry, in soaps. So generally speaking, this is a high priority molecule, and so when you come to naming them, it takes precedence over most other types of organics. So if we look at the homologous series here, we've got methanoic acid as the basic one, ethanoic, propanoic and butanoic. Now in all of these four, you don't need a number to show where the carboxylic acid group is because it's always on the end. So there's no need for a number there. We tend to write Cu if we're writing out the formula, just to show that the carbon here is quite separate from the rest of the carbon chain. Now, if we look at the naming of carboxylic acids which have substituted groups, we can see here that we've got a methyl group. Now, because the carboxylic acid is the most important feature of this molecule, that takes precedence. So that's the main part there, and then you add the 3-methyl to it as a prefix. That's basic ethanoic acid there. This one here has an alkene group. So again, this is butanoic acid. Okay, so once again, this is the priority. In fact, it's a carboxylic acid, and it's a 2-ene, so it's because it's between the second and the third carbon. So that is put between there, just like how we normally name alkenes. Lastly, here we've got two different functional groups. So we've got the chloride, and we've got the alkene. So the alkene's between the 2 position. So this is the 2-pentenoic. And then we've got 4-chloro, so that's on the 4th carbon there. Polarization is important in this molecule, so the reason it's able to lose its hydrogen there to become an acid is because of the electronegativity of this oxygen here. So the electrons are basically forced along and up to this point here, along the molecule. And so what happens eventually is the hydrogen loses all of its electrons and becomes a proton. So this is shown in this reaction here. We don't have to worry about these curly arrows. That's something you look at later on in organic synthesis. But what happens is the OH of a base comes in and steals the proton, and the electrons are absorbed into the molecule here to make a negative. So this is called a conjugate base afterwards, because it would be slightly basic, as in it would be accepting protons because it's got this negative charge.